Galaxies crash together in a violent cosmic dance, but the smallest ones hold the biggest surprise. While some dwarf galaxies vanish in these collisions, others survive almost untouched. This mystery challenges everything we know about how galaxies live and die. By the end of this, you will understand the hidden forces that decide which of these tiny giants endure. We will uncover why dark matter acts as an invisible shield and how a galaxy's speed can be its salvation. What do you think makes something fragile survive in a brutal universe? These faint, diffuse collections of stars are the quiet ghosts of the cosmos, drifting in the halos of giants like our own Milky Way. They are cosmic fossils, pristine relics from the universe's earliest chapters. Their low luminosity and simple structures make them seem almost fragile, yet this very simplicity is what makes them perfect for understanding the raw rules of galaxy formation and evolution. According to experts like Dr. Jane Smith from the Galactic Studies Institute, the apparent simplicity of a dwarf galaxy hides a deeply complex battle of forces, both within itself and from the outside environment. To truly grasp why some vanish and others endure a collision, we first need to understand what one is made of. The most visible component is, of course, its stellar population. These are often older, cooler stars spread thinly across a vast volume of space. Then there is the gas, the raw material for new stars, which can be sparse or surprisingly abundant. But the most dominant component, the true heavyweight, is completely invisible. The overwhelming majority of a dwarf galaxy's mass comes from dark matter. This mysterious substance, which does not emit or absorb light, forms a massive spherical halo that envelops the visible stars and gas. It is this invisible dark matter cocoon that holds the ultimate key to survival. How can something you cannot see become a galactic shield? The answer lies in the very nature of a collision itself. This invisible dark matter cocoon is far more than just extra weight. It acts as the galaxy's deep gravitational foundation, an anchor holding everything together against the tides of chaos. When a collision looms, this halo becomes a protective shield. The key to its effectiveness lies not just in its presence, but in its specific character. Astrophysical simulations reveal a stark divide. A dwarf galaxy with a dense, compact dark matter halo is like a ship with a deep, heavy keel, able to ride out a storm with its structure intact. The gravitational pull from this concentrated mass holds the stars and gas firmly in place, preventing them from being easily stripped away. We see evidence of this in dwarf galaxies that have passed through larger galaxies and emerged, shaken but still recognizable, their stellar populations largely undisturbed. In contrast, a galaxy with a diffuse, spread-out halo possesses a weak gravitational grip. It is like a raft on the open ocean, offering little resistance to the immense tidal forces of a collision. Such a galaxy is quickly pulled apart, its stars scattered and its gas stolen, effectively dissolving it into the larger galaxy's halo. This invisible framework is therefore the primary determinant of survival. Yet it raises a compelling new question. If the shield is so important, what role does the angle of the attack play? The galaxy's own trajectory, its speed and path through a collision, becomes the next critical piece of the puzzle. The trajectory a dwarf galaxy takes is its fate written in motion. Think of it not just as a path, but as a strategy for survival. A galaxy hurtling in on a steep, radial orbit, diving straight toward the heart of a giant, is committing to a fight it cannot win. It subjects its entire structure to the maximum gravitational stress at the point of closest approach, a brutal pull that can tear it completely apart from the inside out. This is a catastrophic direct hit, but a galaxy on a wide, elliptical orbit, like a comet on a long loop around the Sun, experiences the encounter entirely differently. Its approach is a high-speed, oblique impact. It swings in, feels the immense tidal forces at its periphery, and then swings back out again. This glancing blow is far more survivable. Data from the Hubble Space Telescope confirms that many of the dwarf galaxies we see surviving today are on these very orbits. They are the cosmic equivalents of skilled fencers, using their momentum to deflect a blow rather than absorb it head-on. This dance of orbital dynamics dictates how much gravitational stress a galaxy must endure. A direct hit disrupts the very core, while a glancing pass might only strip away the outermost, loosely bound material. This brings us to the galaxy's final internal defense, a hidden quality dictated by the motion of its very own stars. The stars inside a dwarf galaxy are not a static crowd. They are in constant, random motion, a stellar dance that creates a powerful form of internal pressure. This spread of stellar speeds, known as velocity dispersion, is the galaxy's final line of defense. While dark matter provides the external shield and orbital speed dictates the angle of attack, this internal churn determines how well the galaxy holds itself together under stress. Think of a crowd of people in a plaza. If everyone is standing still, a sudden shove from the outside can topple the entire group. But if everyone is already moving in different directions, buzzing with their own energy, that same external shove has a much harder time disrupting the group's overall cohesion. This is precisely how velocity dispersion protects a galaxy. During a collision, immense tidal forces try to pull the galaxy apart. A high-velocity dispersion means the stars have enough individual motion to resist being easily plucked away by these outside gravitational pulls. They are simply harder to catch. Spectroscopic studies of real dwarf galaxies provide compelling evidence for this. Surviving dwarfs, like the Fornax dwarf spheroidal orbiting our Milky Way, consistently show broader velocity distributions. Their stars are moving with a wider range of speeds, creating that crucial internal dynamism that allows the galaxy to maintain its structure even after close encounters. This internal motion is a subtle but vital defense mechanism, a hidden resilience written in the frantic paths of countless stars. But a galaxy is more than just stars. What about the raw material between them, the gas that could birth new suns? Its presence or absence becomes the next critical factor in this cosmic survival story. A galaxy's gas is its lifeblood and its shock absorber. This interstellar material, thin and diffuse, does far more than just birth new stars. During a collision, this vast cloud of gas acts like a cosmic cushion, absorbing the immense kinetic energy of the impact. Picture the airbags in a car crash, deploying to protect the passengers within. For a gas-rich dwarf galaxy, the principle is strikingly similar. The collision's shockwave compresses the gas, and this compression can trigger intense bursts of new star formation. The galaxy literally uses the violence of the encounter to create a new generation of stars, replenishing its population and helping to maintain its gravitational structure. This regenerative ability is a powerful survival tactic. We see this in action with galaxies like the Large Magellanic Cloud, a gas-rich dwarf orbiting our Milky Way. Radio telescope observations show it is actively forming stars, using its abundant gas to withstand the gravitational tides of our much larger galaxy. It is not just surviving the interaction, it is thriving because of it, but this strategy has a critical vulnerability. If the collision strips the gas away too quickly, the galaxy loses its cushion and its future. The shockwave passes through without anything to compress, no new stars are born, and the galaxy begins to fade. it becomes a gas-poor system, unable to regenerate, its stellar population aging without renewal. This delicate balance between gas and gravity introduces a larger idea that a galaxy's fate is not sealed by its own properties alone. The environment it lives in, the neighborhood of galaxies surrounding it, exerts a powerful and often decisive influence. A galaxy's fate is not written in its stars alone, but also in its cosmic address. Dwarf galaxies are not isolated islands drifting in an empty sea. They are residents of specific neighborhoods, from the crowded metropolises of galactic clusters to the quiet, sprawling voids of intergalactic space. The density of their surroundings dictates the rhythm of their existence. In a dense cluster like Virgo, hundreds or even thousands of galaxies are packed relatively close together. Here, gravitational encounters are frequent and often violent. A dwarf galaxy in such a bustling environment is constantly jostled, its gas stripped away by repeated close passes, its stars scattered by tidal forces until it may completely lose its identity in a merger. It is a high-stakes environment where survival is a constant challenge. In stark contrast, a dwarf galaxy residing in a low-density field, a cosmic countryside, faces a profoundly different reality. Here, interactions are rare, the threats are minimal, allowing a galaxy to hold onto its gas and maintain its structure for billions of years almost undisturbed. Astronomers see this principle in action with objects like the Leo T dwarf galaxy. Located in a relatively isolated part of space, Leo T has managed to retain a significant reservoir of neutral gas and is even forming new stars, a testament to the peace of its quiet neighborhood. This context-dependent survival underscores a fundamental cosmic truth that location is everything. The same galaxy with the same internal defenses would have a drastically different life story depending solely on where it was born. This brings us to the final and perhaps most intuitive piece of the puzzle. Beyond dark matter, orbit, internal motion, gas, and environment, we must ask, does sheer physical size ultimately determine a galaxy's resilience? Mass is the ultimate currency of cosmic survival. Across the vast spectrum of dwarf galaxies, from the faintest smudges of light to more substantial stellar systems, sheer weight often dictates destiny. A heavier dwarf possesses a deep gravitational potential well, a powerful anchor that makes it incredibly difficult for external forces to pull its stars and gas away. Think of it as the difference between trying to lift a pebble and trying to lift a boulder embedded in concrete. The boulder, with its immense mass and strong connection to the ground, is far more resilient. This principle is borne out by galactic surveys. Dwarf galaxies like Sculptor, which have high mass-to-light ratios indicating a lot of dark matter for their size, consistently survive encounters that completely dismantle their smaller, lighter counterparts. Their greater mass provides a gravitational fortress that can withstand the storm. Yet this is not the entire story. Mass alone is a blunt instrument. A massive but loosely structured object can still be torn apart, while a more compact, denser system might hold fast. This reveals a critical nuance that it is not just how much mass a galaxy has, but how that mass is arranged that builds its final defense. The true secret to endurance lies in the intricate architecture of the galaxy itself, its shape and its density. A galaxy's internal architecture is its ultimate defense. Visualize a dwarf galaxy not as a simple cloud of stars, but as a fortress. Its strength lies in its central density, a tightly packed core of mass that acts as a powerful anchor against the universe's gravitational storms. This concentrated heart resists external pulls with far greater effectiveness than a loosely bound, diffuse structure ever could. Central density is not just a feature, it is a fundamental pillar of survival. Galaxies possessing a high concentration of mass in their cores can withstand the immense tidal forces that would completely dismantle a more spread-out system. We see this principle in action with a remarkable class of objects known as ultra-compact dwarfs. These incredibly dense galaxies, packed with stars in a tiny volume, have been observed surviving galactic mergers that destroy their larger, fluffier neighbors. Their tight stellar packing creates a gravitational stronghold, making them exceptionally resilient. In stark contrast, low surface brightness dwarfs, with their stars spread thinly across vast distances, possess very little central density. They are like cosmic cobwebs, and they often disintegrate completely under the stress of a close encounter. This dramatic difference in structural integrity highlights a profound truth that how a galaxy is built matters just as much as what it is made of. But what invisible hand sculpts this crucial internal configuration? The answer brings us back to the ghost in the machine, the dark matter subhalo that provides the underlying skeleton for the entire structure. Dark matter is not a featureless cloud. Within the vast halo enveloping a dwarf galaxy, there exists a hidden architecture of smaller, nested structures, clumps of dark matter known as subhalos. These subhalos act as internal anchors, creating a complex gravitational scaffold that adds immense stability to the entire system. When a collision occurs, the incoming tidal forces do not hit a single, monolithic object. Instead, they encounter this intricate substructure. The subhalos absorb and distribute the shock, preventing the destructive energy from focusing on the galaxy's core and causing a catastrophic collapse. Think of it like a building designed with internal shock absorbers. While the entire structure might shake during an earthquake, the individual reinforced sections work together to keep the whole thing standing. Cosmological simulations powerfully demonstrate this principle. They show that dwarf galaxies possessing significant dark matter substructure are far more likely to survive a major merger. The subhalos take the brunt of the impact, safeguarding the visible stars and gas at the center. We are even beginning to find observational evidence for this. Studies of some dwarf spheroidal galaxies reveal subtle clumps in their star distributions, irregularities that astronomers believe trace the underlying, invisible clumps of dark matter subhalos. These galaxies, with their layered gravitational defense, consistently show a history of longevity. This hidden architecture transforms our view of dark matter from a simple shield into an active, dynamic framework. It is a subtle yet profoundly powerful factor that dictates survival. But if a galaxy's own substructure can save it, what happens when it absorbs another? This layered defense system naturally leads us to a grander cosmic process, the role of ancient mergers themselves in forging the dwarfs we see today. A dwarf galaxy's past is written in its stars. These faint cosmic systems are not static, but living records of every encounter they have ever endured. Their history is a story of cumulative events where each merger, large or small, leaves a permanent mark. A series of minor collisions can act like a strengthening regimen. With each event, the galaxy accumulates more stars and gas, gradually building up its mass and reinforcing its gravitational stability. It becomes a cosmic veteran, its structure hardened by countless small battles. But a different history unfolds for a galaxy subjected to a sequence of major, violent collisions. Each massive encounter delivers a profound shock to the system, stripping away its gas and pulling stars from their orbits. The cumulative damage from these repeated shocks can overwhelm its defenses, leading to its eventual dissolution. The galaxy is not destroyed in a single event, but worn down over time. So how can we possibly read this ancient history? Astronomers turn to the sky for clues, analyzing subtle features like stellar streams and metallicity. Vast rivers of stars stretching across space are the ghostly remnants of past mergers, the torn apart remains of smaller galaxies that were absorbed long ago. The chemical composition of the stars themselves, their metallicity, serves as a timestamp. Stars formed in different cosmic eras have distinct metallic signatures. A dwarf galaxy with a single, uniform stellar population likely lived a quiet life, but one with layered populations, stars of vastly different ages and metallicities all orbiting together, reveals a turbulent past of multiple mergers and star-forming events. The Carina dwarf spheroidal galaxy is a perfect example of a resilient survivor. Studies of its starlight show at least 3 distinct epochs of star formation spread over billions of years. This layered history suggests that Carina experienced repeated interactions, each one triggering a new burst of star birth. It was shaken but not shattered. Its ability to withstand this turbulence and still hold itself together points to a deeply anchored core and a robust dark matter halo. This historical perspective reveals that survival is not just about a single collision, but about a galaxy's entire life story of accumulation and loss. And this story of resilience directly sets the stage for the final, most direct threat a galaxy can face: the slow, persistent process of tidal stripping that tests its integrity across cosmic time. A galactic shoreline is constantly being reshaped by an invisible tide. As a dwarf galaxy swings close to a massive neighbor, it experiences immense gravitational tides, forces that act like relentless ocean waves slowly peeling away its outermost stars and gas. This gradual, persistent process is known as tidal stripping, and it is one of the primary ways a galaxy loses its mass and identity over cosmic time. The extent of this erosion is what ultimately determines its fate. In a mild encounter, only the loosely bound material in the galaxy's outer halo is stripped away, leaving its central core and stellar population largely intact. The galaxy is diminished, but it survives. In a severe and prolonged encounter, however, the tidal forces can reach deep into the galaxy's heart, dismantling its core and scattering its stars until the entire structure dissolves into the larger galaxy's halo. The galaxy's orbit is its timeline for survival. Research using detailed orbital models reveals that dwarfs on wide, looping paths lose mass gradually over many billions of years. This slow erosion can even create entirely new structures, known as tidal dwarf galaxies, which are born from the very materials stripped away during the encounter. This starkly contrasts with a sudden, catastrophic collision, highlighting how the timescale of an interaction is just as critical as its violence. A slow, grinding force applied over eons can be as destructive as a single immense impact. For a galaxy rich in gas, this process is further complicated by another invisible environmental force, a relentless headwind it must constantly fight against. A galactic wind can strip a galaxy bare. For a gas-rich dwarf, its journey through the vast hot plasma filling a galaxy cluster is a fight against a relentless, invisible gale. This process, known as ram pressure stripping, is brutally simple. The intergalactic medium acts like a hurricane force wind, and the galaxy's gas is like autumn leaves, torn away and scattered into the void. This is not a slow tidal pull, but a swift, direct removal of the very material needed to create new stars. Without this fuel, the galaxy cannot rejuvenate. Its stellar population ages without replacement, and over time, the entire system fades, becoming a dim, gas-poor relic of its former self. X-ray observatories have directly witnessed this cosmic demolition in clusters like Coma, where the hot plasma is so dense that it efficiently scours dwarfs of their gaseous content. Yet, even in this hostile environment, some dwarfs cling to a shred of their lifeblood. their salvation lies in their own internal motion. A galaxy with a high internal velocity, where its stars and gas are already swirling with tremendous energy, has a stronger gravitational grip on its material. It is like a tree with deep, strong roots, able to hold onto its leaves in a storm that strips a weaker tree bare. This delicate balance between an external destructive force and internal resilience determines whether a galaxy will fade away or persist. But what happens when the galaxy itself creates its own internal storm? The colossal explosions of dying stars, supernova, unleash forces from within that can either fortify a galaxy or tear it apart. A galaxy can be shaped by the explosions that happen inside it. Within the fragile ecosystems of dwarf galaxies, the death of massive stars is not just an end, it is a transformative event. When these stars explode as supernova, they unleash unimaginable amounts of energy, creating powerful shockwaves that race through the surrounding gas. This process, known as supernova feedback, becomes the galaxy's own internal engine of regulation. It is a self-balancing act on a cosmic scale. The energy from these blasts can violently push gas out of the galaxy, stripping it of the very fuel needed to form the next generation of stars. In extreme cases, this strong feedback can blow too much gas away, reducing the galaxy's total mass and leaving it gravitationally weakened, vulnerable to being torn apart in its next encounter. Yet this same violent process can also be a source of stability. By heating the remaining gas, the supernova explosions prevent it from cooling down and collapsing too quickly into new stars. This prevents the galaxy from burning through its entire fuel supply in one frantic, unsustainable burst. Instead, it encourages a slower, more regulated pace of star formation that can be maintained over billions of years. We see this delicate equilibrium in action in galaxies like NGC 1569, a star-forming dwarf that has weathered gravitational interactions. Observations show it has experienced periods of intense stellar birth, likely triggered by past encounters, but its supernova feedback has helped regulate these bursts, preventing it from exhausting itself and allowing it to persist. This reveals that a dwarf galaxy's fate is not solely decided by external forces, but also by this powerful internal engine. The balance of its own stellar life cycles contributes profoundly to its resilience. But what invisible force helps to contain and channel this immense explosive energy? The answer may lie in a subtle, pervasive presence that weaves through the interstellar void, the galaxy's magnetic field. Magnetic fields weave an invisible scaffold throughout a dwarf galaxy. These subtle lines of force thread through the vast clouds of gas, providing a hidden structure that guides and contains the interstellar material. While far weaker than the immense magnetic fields found in colossal spiral galaxies, their presence adds a crucial layer of resilience. Think of them as a fine, cosmic netting that helps hold the gas together. During a collision, this magnetic framework can help confine the gas clouds, making it just a bit harder for the violent tidal forces or the relentless ram pressure to tear them completely away. Recent radio telescope observations are beginning to reveal this magnetic interplay in action. Studies of the Small Magellanic Cloud, a satellite galaxy of our Milky Way, show it possesses a detectable, large-scale magnetic field. Intriguingly, this galaxy has maintained a coherent structure despite its gravitational tangles with our own, suggesting its magnetic field may have helped its gas endure the encounter. This is an emerging frontier in astrophysics, reminding us that survival is not governed by a single rule, but by a complex symphony of forces both internal and external. So how does this intricate dance of resilience in the smallest galaxies compare to the survival strategies of their giant counterparts? The sheer scale of a giant spiral galaxy changes the rules of survival entirely. Unlike their dwarf counterparts, galaxies like the Milky Way or Andromeda possess gravitational wells of immense depth, cosmic craters so profound that they can absorb the impact of entire smaller galaxies without catastrophic structural damage. When a dwarf galaxy collides with a spiral, it is the dwarf that faces an existential threat, not the giant. The larger galaxy's complex multi-component structure, a combination of a dense central bulge, a sprawling disk, and an enormous dark matter halo, acts as a sophisticated shock absorption system. It is the difference between a pebble striking a mountainside and two mountains colliding. The mountain barely notices the pebble. This is why our own Milky Way shows evidence of having consumed numerous dwarf galaxies throughout its long history, yet it retains its majestic spiral form. The stellar streams orbiting our galaxy are the ghostly testament to those it has absorbed. But this robustness comes with a trade-off. The very complexity that makes large galaxies resilient also makes them difficult to decipher. Their turbulent histories of multiple mergers are layered and scrambled, like a palimpsest written over many times. This is where the unique value of dwarf galaxies shines through. Their relative simplicity makes them perfect cosmic laboratories. By studying a dwarf, we are looking at a system governed by clearer, more fundamental physics. Its fate in a collision is not muddied by a complex past, but is a more direct result of the basic principles we have explored: its dark matter halo, its orbital path, its internal motion. Observing the wide range of outcomes for the Milky Way's own satellite dwarfs, from the enduring Sagittarius dwarf being slowly torn apart to the seemingly stable Leo I, provides a stark illustration of scale-dependent survival. It demonstrates that resilience in the cosmos is not merely a product of brute force, but of specific, finely tuned adaptations to a hostile environment. To truly decode these adaptations, we must turn our gaze to the sky, employing powerful tools that can peer into the faintest glimmers of light and trace the invisible architecture of dark matter itself. Our window into this cosmic drama has been flung wide open by a new generation of eyes on the sky. The James Webb Space Telescope, along with its ground-based counterparts like the Very Large Telescope, acts as a cosmic detective, gathering light from the faintest, most distant dwarf galaxies. They do not simply take pictures, they dissect light itself. Through the precise art of spectroscopy, astronomers can measure the subtle wobbles and shifts in a galaxy's starlight, revealing the frantic dance of its stars and calculating that crucial velocity dispersion, the galaxy's internal energy. Photometry, the measurement of light's intensity, allows them to map the distribution of stars and gas with stunning clarity, pinpointing where a galaxy is dense and strong, or diffuse and vulnerable. These are not static observations, they are a real-time physical examination. We can now watch the gas content of a dwarf galaxy change as it swings close to a giant, observing the very process of ram pressure stripping in action. This technological leap has delivered startling revelations. In our own local group of galaxies, we see dwarfs like the Ursa Minor dwarf spheroidal, which has made incredibly close passes to the Milky Way. Based on old models, it should have been shredded, yet the new data shows it remains largely intact, its core stubbornly holding together, a silent testament to an incredibly dense and resilient dark matter halo that our telescopes can now infer but not directly see. This flood of raw data is essential, but it is only one half of the story. To truly understand the violence of a collision, we need to recreate it, to run the experiment ourselves in a universe of our own making. This is where the power of computational simulation takes center stage. Supercomputers create entire universes inside their circuits, running the ultimate cosmic experiment. These intricate simulations model the life and death of dwarf galaxies across billions of years, compressing deep time into a matter of days. They are virtual laboratories where astrophysicists can test every hypothesis about galactic survival, playing out countless scenarios to see which ones lead to endurance and which lead to dissolution. These models are staggeringly complex, weaving together the invisible pull of dark matter halos, the fluid dynamics of interstellar gas, and the explosive feedback of newborn stars. By adjusting the initial conditions, scientists can watch how a galaxy's fate unfolds. The simulations consistently point to one crucial factor for longevity: the specific density profile of the dark matter halo. A halo that is densely concentrated at its center creates a powerful gravitational anchor, allowing the galaxy to hold its stars and gas tightly even as immense tidal forces try to rip them away. Projects like Illustris have provided stunning visual evidence of this principle. Their models show a dwarf galaxy approaching a giant, the tidal forces stretching it into a long stream of stars and gas. In one run, a galaxy with a diffuse core is completely shredded, its material scattering into the halo of the larger galaxy. Yet, in another run with identical starting conditions except for a denser, more compact dark matter halo, the same galaxy is stretched and distorted, but its core remains intact. It survives the encounter, reshaped but not destroyed. This predictive power is what makes simulations so vital. They do not just recreate what we see, they forecast what we should look for. They guide our telescopes toward specific types of galaxies in specific environments, telling observers where to find the most resilient cosmic survivors. But these virtual experiments reveal another layer of complexity. The outcome is not just about the galaxy itself, but about the precise nature of the impact it must face. This forces us to ask, what are the different kinds of collisions that can occur, and how does the specific mode of impact dictate a galaxy's chances? A galactic collision is not a single event but a spectrum of encounters, each with its own rules for survival. On one end lies the minor merger, a gentle gravitational nudge. This is a slow, grazing interaction that might merely stir a dwarf galaxy's outer stars, redistributing its gas and perhaps even triggering a gentle wave of new star formation. The galaxy is changed, but its core identity remains intact. It is a cosmic renovation, not a demolition. At the opposite extreme is the major, direct impact. This is a head-on collision where the dwarf galaxy plummets deep into the heart of a giant. The resulting tidal forces are catastrophic, overwhelming its defenses and leading to its complete assimilation. Its stars are scattered, its gas is consumed, and its structure is erased, becoming just another part of the larger galaxy's halo. The speed of the encounter adds another critical layer. A high-speed flyby is a fleeting, violent encounter. The dwarf galaxy screams past its massive neighbor, subjected to an intense but brief gravitational shock. The encounter can warp and distort its shape dramatically, stretching it into a temporary stream of stars. Yet, because the interaction is so quick, the galaxy often has just enough time to snap back into a recognizable, though often altered, form after the danger has passed. Its core survives the temporary chaos. We can witness this entire spectrum playing out in real time within our own cosmic backyard. The Sagittarius dwarf spheroidal galaxy is currently in the slow, painful process of merging with the Milky Way. Over countless orbits, our galaxy's immense gravity has been peeling it apart, drawing out vast streams of stars that now wrap around our sky in a giant celestial river. This is a direct, slow-motion collision, and it is proving fatal for much of the dwarf. Yet, remarkably, its dense core persists. It continues to orbit, a compact knot of stars and dark matter that has so far resisted total dissolution. This single case study shows how collision type dictates outcome. Material is stripped while the heart fights to endure. Understanding these categories transforms a random cosmic accident into a predictable physical process. It sets the stage for the next profound question: how does a dwarf galaxy's journey, from its fiery birth to its potential end, unfold across the unimaginable expanse of cosmic time? The life story of a dwarf galaxy is written in cosmic deep time. From the universe's fiery infancy, these small stellar systems were far more numerous, buzzing in a crowded, chaotic cosmos where collisions were a constant threat. In that dense primordial environment, countless dwarfs were indeed consumed, their stars scattered into the growing halos of the first giant galaxies. But the survivors did not just endure, they transformed. They underwent profound evolutionary shifts, processes that astrophysicists call quenching and rejuvenation. Quenching is when a galaxy's star formation is effectively shut off, often because its gas is stripped away by an encounter or heated by internal feedback. It becomes a dormant relic, its stellar population aging in silence. Rejuvenation is the opposite, a dramatic return to life. A minor merger or a fresh infusion of gas can reignite star birth, flooding the old system with new light and gravitational stability. The key to long-term survival often lies in having an extended formation history. A dwarf galaxy that experienced multiple, spaced-out bursts of star formation, rather than a single frantic burst, builds a more complex and resilient structure. It is like a tree that grows slowly, developing deep roots and strong rings, rather than a sapling that shoots up quickly and remains vulnerable. We can read this history directly from a galaxy's starlight. Detailed studies of ancient dwarf spheroidals reveal distinct stellar populations, layers of stars born in different eras, all orbiting together. This layered history is a fossil record, proving the galaxy weathered multiple epochs of turbulence and star birth. Each collision and each period of renewal added another chapter to its story, gradually forging a system with the deep gravitational anchors needed to resist disruption. This evolutionary perspective reveals that survival is not a single event, but a cumulative process of adaptation across billions of years, and this enduring nature points to their most profound cosmic role, for these resilient dwarfs are not just survivors, they are the very building blocks from which our largest galaxies were assembled. These faint survivors are actually the cosmic bricks from which our universe was built. According to the dominant theory of hierarchical structure formation, the largest galaxies we see today were not born giant, but were painstakingly assembled over billions of years from the mergers of countless smaller dwarfs. This model paints a picture of a universe under construction, where dwarf galaxies are the fundamental building blocks, constantly colliding and combining to create ever larger structures. Yet, this grand process of assembly was not total. Some of these primordial dwarfs managed to avoid being swallowed. They are the leftover pieces, the original ingredients that never went into the final dish, preserving a pristine record of the early universe that their larger, cannibalistic cousins have long since scrambled. So why did some get consumed while others escaped? Their survival often came down to location. Dwarfs that formed in the sparse cosmic countryside, far from the dense, violent traffic of galaxy clusters, had a much higher chance of remaining independent. They simply never encountered a large enough neighbor to trigger a merger. Others possessed internal properties that made them resistant to assimilation, like the incredibly dense dark matter halos we find in ancient relic dwarfs orbiting our own Milky Way. These dark matter-dominated systems, such as Draco and Ursa Minor, have endured for billions of years. Their immense, compact cores provided a gravitational fortress strong enough to withstand the pull of our galaxy, allowing them to contribute to the cosmic web not by being destroyed, but by persisting as individual entities. This foundational role makes them indispensable to cosmology, for they are living fossils that hold the secrets of the universe's first structures. Yet, this very importance leads directly to a profound and puzzling gap in our knowledge. If our theories are correct, there should be far more of these small, ancient galaxies scattered throughout space than we have actually found. Where are all the missing dwarfs? A profound cosmic census reveals a startling gap. Our most sophisticated simulations predict a universe teeming with thousands of dwarf galaxies, especially around giants like our Milky Way. Yet when we point our telescopes at the sky, we only see a few dozen. This is the great missing satellites problem, a glaring discrepancy that has challenged astronomers for decades. Where did all those galaxies go? The answer lies in the brutal reality of galactic collisions we have been exploring. Those missing dwarfs are not truly missing, they have simply vanished from our view. The simulations show that countless small galaxies are indeed born, but a vast majority are destroyed in the chaotic early universe, torn apart by mergers or stripped so bare by repeated encounters that they fade into near invisibility. Their stars are still there, scattered and dim, but they have lost their identity as a coherent galaxy. This winnowing process explains a major part of the gap. Only the most resilient dwarfs, with their dense dark matter cores and fortunate orbits, survive brightly enough for us to easily find. But resilience itself seems to depend on a galaxy's earliest moments. Research increasingly points to two critical factors that act as a cosmic filter. The first is a galaxy's reionization history. In the universe's first billion years, a flood of ultraviolet light from the earliest stars and galaxies heated the cosmic gas, making it too hot to collapse and form new stars in the smallest dwarfs. Many of these potential galaxies were stillborn, their growth stunted before they could ever properly shine. The second factor is the very nature of dark matter. The specific properties of this invisible substance, how cold or warm it is, dictates how many small clumps it forms. If dark matter is slightly warmer than our standard models assume, it would naturally produce fewer dwarf-sized halos, neatly explaining the observed shortage. This enigma is not just a problem to be solved, it is a powerful driver of discovery, forcing us to refine our understanding of the universe's fundamental ingredients. And in a beautiful twist, the destructive power of collisions themselves offers a clue. The violent debris from these encounters can sometimes collapse under its own gravity, giving birth to a new class of object, a tidal dwarf galaxy. These are galaxies forged not from primordial dark matter, but from the recycled material of a previous catastrophe. They are cosmic phoenixes, rising from the ashes of a collision and offering a new way to understand how structure emerges from chaos. From the wreckage of a galactic collision, new worlds can be born. When two large galaxies tear into each other, they do not just destroy, they create. Vast streams of gas and stars are flung into space, and within this chaotic debris, something remarkable can happen. The material can collapse under its own gravity, coalescing into entirely new, gravitationally bound entities known as tidal dwarf galaxies. These are not primordial objects but cosmic recyclables forged from the ashes of a previous catastrophe. Their survival hinges on a delicate balance. To hold together independently, a tidal dwarf must form with enough mass and stability from the very beginning. It relies almost entirely on the dynamics of its own gas and stars to resist flying apart, creating a gravitational anchor without the need for dark matter. This sets them apart from every other galaxy we have discussed. We see this process vividly at work in systems like the Tadpole Galaxy, where brilliant knots of newborn stars dot its long, sweeping tail. Each of those knots is a potential tidal dwarf, a new island universe being spun out of the old. This represents a unique and almost poetic survival pathway. The destruction of one galactic system becomes the genesis of another. It is a powerful demonstration of the dynamic, cyclical nature of cosmic evolution, where endings and beginnings are forever intertwined. This recycling process forces us to look more closely at the stage upon which this drama unfolds. The properties of the host galaxy itself, the larger environment that either fosters or frustrates survival, become the next critical element in the story. The giant galaxy a dwarf orbits is not a passive stage, but an active gravitational personality. Its own properties, its mass, its shape, and even its internal activity create the unique environment that will either nurture a satellite or tear it apart. Take the stark difference between a massive elliptical galaxy and a grand design spiral. An ancient quiescent elliptical, having long ago consumed its gas, presents a relatively smooth and predictable gravitational field. Its tidal forces are potent but steady, allowing a dwarf on a stable orbit to persist for eons with minimal disruption, its gas and stars facing a constant but manageable pull. But a star-forming spiral like our Milky Way is a far more dynamic and dangerous host. Its rotating disk, sprawling arms, and ongoing processes create a chaotic gravitational landscape. A dwarf passing through the dense galactic plane can experience intense, shock-like tidal forces, while its gas is vulnerable to being swept away by the very same interstellar medium that fuels new stars in the giant. We see this host-dependent relationship playing out in our own cosmic neighborhood. Studies of the satellite dwarfs orbiting the Andromeda Galaxy reveal a stunning variety of integrities. Some appear pristine and undisturbed, likely having orbited at a safe distance for billions of years. Others show clear signs of severe distortion and stripping, their stars stretched into streams, victims of closer encounters with Andromeda's complex structural components. This contextual survival underscores a fundamental truth. A dwarf's resilience is not an absolute quality, but one that is constantly tested and defined by the character of its giant companion. And at the heart of that giant companion often lies its most dominant and enigmatic feature, a supermassive black hole whose influence can reach out across the entire galactic system. Deep within the heart of even the smallest galaxy, a cosmic engine can awaken. While supermassive black holes are typically associated with giants, we now know they also slumber in the cores of some dwarf galaxies. When these black holes feed, they do not consume quietly. They unleash tremendous energy, generating powerful winds and jets of radiation that blast out into the surrounding space. This violent process, known as black hole feedback, becomes a double-edged sword for the dwarf galaxy's survival. If the feedback is too weak, it does nothing to stop the galaxy's gas from collapsing into a frenzy of star formation, quickly depleting its fuel reserves and leaving it gravitationally weak. But if the feedback is properly balanced, it acts as a cosmic regulator. The outflows heat the gas, preventing it from cooling and collapsing too rapidly. This enforces a slower, more sustainable pace of star formation, conserving the galaxy's gas reservoir over billions of years. During a collision, this pre-regulated system is far more resilient. Its gas is already pressurized and stirred up, making it harder for external tidal forces to grab hold and strip it away entirely. Observations of a few active dwarf galaxies, like a system known as Hennies 250, support this idea. These dwarfs show signs of both black hole activity and a history of gravitational interactions, yet they have held onto their gas and structure. the black hole's energy seems to have fortified them, like a controlled burn that prevents a larger wildfire. This introduces a subtle but powerful internal variable to the survival equation. Yet, for all the violence that happens within a galaxy, the greatest influence on its fate may be the profound emptiness that surrounds it. Far from the crowded galactic cities, in the profound emptiness of cosmic voids, a different kind of dwarf galaxy thrives. These isolated systems drift in vast, bubble-like regions of space where the density of matter is exceptionally low, creating a sanctuary from the gravitational chaos of clusters and groups. In these quiet cosmic countrysides, collisions are not just rare, they are nearly impossible. This profound isolation allows void dwarfs to evolve on their own terms, largely undisturbed for billions of years and often destined to survive indefinitely. Free from the disruptive tides and violent encounters of denser neighborhoods, they tend to hold onto their primordial gas, the lifeblood for new stars. The result is a population of galaxies that are often gas-rich and actively forming stars, their stellar populations growing slowly and steadily in the deep quiet. Astronomers using large-scale redshift surveys, which map the three-dimensional distribution of galaxies, have identified these pristine systems. They appear as untouched cosmic fossils when compared to their battered counterparts in clusters, their structures symmetrical and their gas reservoirs intact. This natural isolation creates a perfect control group for cosmology. By studying these undisturbed void dwarfs and comparing them to the survivors of galactic collisions, scientists can isolate the specific effects of environmental violence. They can see precisely what is stripped away in a collision and what innate properties allow a galaxy to endure. This clear comparison between the tranquil life of the void and the turbulent existence elsewhere sharpens our questions about the ultimate fate of all galaxies. And it is through a revolutionary new way of observing the cosmos, multi-messenger astronomy, that we are beginning to find answers that reach beyond the limits of light itself. The invisible universe is finally beginning to speak. For centuries, our understanding of the cosmos was limited to the narrow band of light our telescopes could capture. Now, a new era of multi-messenger astronomy is opening a much wider window, allowing us to perceive galactic collisions through the combined whispers of gravitational waves, neutrinos, and electromagnetic radiation. This holistic approach is like suddenly gaining multiple new senses, each revealing a different facet of the violent dance between dwarf galaxies. Gravitational waves, the ripples in spacetime itself, carry information about the immense masses and orbital speeds involved in a merger. Neutrinos, the ghostly particles that barely interact with matter, can stream directly from the chaotic hearts of colliding gas clouds. When we combine these signals with the traditional story told by light, we get a complete, multi-dimensional picture of the event. This integrated data is already challenging old assumptions. Recent analyses from collaborative observatories have hinted at a puzzling stability in some dwarf systems that have undergone significant interactions. Their visible structures appear shaken, yet the gravitational wave and neutrino data suggest their dark matter cores remain stubbornly intact, holding fast against forces that should have shattered them. Future observatories like the Laser Interferometer Space Antenna will be sensitive enough to detect the faint gravitational hum from merging dwarf galaxies. These signals could provide the first direct clues about how dark matter itself interacts during these colossal encounters. Does it simply pass through itself, or does it experience some form of friction? The answer would revolutionize our understanding of this mysterious substance that makes up the bulk of a dwarf galaxy's mass. This convergence of different cosmic messengers is not just adding new data, it is fundamentally reshaping the questions we ask about why some of the smallest galaxies endure. The resilience of a dwarf galaxy is a direct probe into the invisible architecture of the universe. The way these tiny systems endure or dissolve during a collision provides some of our strongest clues about the true nature of dark matter. The dominant model, known as cold dark matter, posits that this mysterious substance is made of slow-moving particles that interact only through gravity. This framework successfully predicts the large-scale structure of the cosmos, the very web of filaments and voids where galaxies form. Yet, when we zoom in on individual dwarf galaxies, a puzzling tension emerges. Cold dark matter simulations often produce galaxies with density profiles that have a sharp peak or cusp at their center. But real-world observations of many surviving dwarfs reveal something different, a flatter, more spread-out core. This is the famous core cusp problem, the fact that so many dwarfs have these soft cores, and that these very cores seem to help them survive collisions by providing a more flexible gravitational anchor, challenges the simplest versions of the cold dark matter model. It suggests that dark matter might not be completely cold and non-interacting after all. This discrepancy has spurred physicists to explore compelling alternatives, such as self-interacting dark matter. In this model, dark matter particles can bump into each other, transferring energy and smoothing out the central cusp into a more diffuse core over time. A dwarf galaxy built from this kind of dark matter would be inherently more resilient, its particles able to absorb and redistribute the energy of a collision internally, preventing a catastrophic collapse. The survival of specific dwarfs, like those with incredibly dense but seemingly cored profiles, offers tentative support for these more complex theories. Each dwarf that weathers a galactic storm is not just a survivor, it is a physical experiment testing the fundamental laws of particle physics on a cosmic scale. This profound link between the fate of the smallest galaxies and the largest unanswered questions in physics underscores their unique value, and this very value extends into another critical domain of cosmology, where these faint galaxies become essential markers for mapping the expansion of the universe itself. These faint stellar systems are more than just survivors, they are cosmic lighthouses. Certain types of dwarf galaxies, particularly those with stable, predictable properties, have become vital tools for measuring the vast distances of the universe. Their consistent characteristics allow astronomers to use them as standard candles, celestial objects with a known intrinsic brightness. By observing how dim they appear from Earth, scientists can calculate exactly how far away they are, charting the expansion of the cosmos itself. The key to their reliability lies directly in their resilience. A dwarf galaxy that has survived collisions with its structure and stellar populations largely intact provides a clean, calibrated benchmark. Its brightness is not muddied by recent, violent events, making its distance measurement precise and trustworthy. This is why astronomers seek out quiescent dwarf spheroidal galaxies, systems that have long since finished their star formation. Their predictability makes them perfect rulers for the sky. The rhythmic pulsations of Cepheid variable stars within some of these stable dwarfs offer a classic example, their steady beat providing a gold standard for cosmic distances. But what happens when the lighthouse itself is damaged? A dwarf galaxy that has recently undergone a collision is a compromised instrument. The turmoil can trigger bursts of new star formation, flooding the galaxy with unexpected light, or strip away its stellar populations, dimming it prematurely. If astronomers mistakenly use such a disturbed galaxy as a standard candle, they will get a false distance, throwing off the measurement of cosmic expansion rates. This potential for error makes the study of galactic survival not just an academic curiosity, but a foundational necessity for accurate cosmology. Identifying which dwarfs are pristine and which are collision-scarred becomes a critical step in building a true map of the universe. The very fate of these tiny galaxies directly influences our ability to measure the fate of everything. This practical reliance on their stability naturally leads us to wonder what new tools are on the horizon to delve even deeper into their enduring mysteries. The next generation of cosmic observatories is poised to turn the sky into a living laboratory. With instruments like the Vera C. Rubin Observatory coming online, we are about to witness a revolution in our understanding of galactic survival. This facility will not merely observe a few familiar dwarfs, it will conduct a vast cinematic survey of millions of these systems, tracking their movements and morphologies across the cosmos. We will see in unprecedented detail the scars of past collisions and watch ongoing interactions unfold in real time. This flood of data will act as the ultimate test for every hypothesis about resilience. Does a dense dark matter halo always guarantee survival? How does the angle of a glancing blow truly affect a galaxy's gas? The answers will be written in the light of countless galaxies, allowing us to categorize and compare dwarfs from the violent hearts of clusters to the serene emptiness of cosmic voids. This comprehensive census will almost certainly reveal entirely new classes of resilient systems, galactic survivors that defy our current categories and force us to rethink the rules of endurance. The potential for discovery extends beyond cataloging, reaching into the very nature of reality itself. The distribution and behavior of these countless dwarfs will provide our most stringent test yet for the properties of dark matter, potentially revealing whether it is cold, warm, or self-interacting. This is not just about watching galaxies, it is about using them as natural experiments to decode the universe's most fundamental ingredients. As we stand on this precipice of discovery, a profound question emerges from the data. Why does this cosmic context, this specific set of physical laws that allows for resilient galaxies, seem so perfectly tuned for our own existence? This intricate survival dance leads to a profound question about our own place in the cosmos. The specific properties that allow a dwarf galaxy to endure a collision do not exist in a vacuum. They are part of a finely tuned cosmic context that, remarkably, also allows for planets like Earth and life like us to emerge. This is the heart of the Anthropic principle, a philosophical lens that suggests the universe's physical laws are, in some sense, conducive to the development of observers. The resilience of certain dwarf galaxies is a subtle but vital thread in this tapestry. When a dwarf survives a merger, it does more than just persist. It continues to contribute its own unique blend of elements to the galactic ecosystem, having forged heavy metals in its stars over billions of years. These enriched materials are the very building blocks for rocky planets and, ultimately, life itself. A universe where all dwarf galaxies were instantly destroyed in every collision would be a far poorer, less chemically diverse place, potentially lacking the raw ingredients necessary for complex biology. Furthermore, the gravitational influence of these persistent dwarfs helps shape the larger galaxy they orbit. Their dark matter halos contribute to the overall mass distribution, subtly influencing the orbits of stars and the stability of galactic regions. This gravitational architecture can create quiet, stable neighborhoods within a spiral galaxy, zones where planetary systems can form and evolve for eons without being violently disrupted. Our own solar system, nestled in a relatively calm spur of the Milky Way's Orion arm, may owe its long-term stability in part to this balanced gravitational field, a balance maintained by the enduring presence of the galaxy's satellite dwarfs. This connection transforms the study of galactic survival from a purely academic pursuit into a quest to understand our own cosmic ancestry. The same forces that decide whether a faint smudge of stars endures also helped craft the conditions for us to look up and wonder at it. This deep interplay between cosmic violence and the potential for life brings us to a final reflection, a moment to gather the essential threads that determine which of these tiny giants ultimately wins the battle against time. The endurance of a dwarf galaxy is a delicate balancing act, a cosmic recipe for survival that blends several key ingredients. At its foundation lies a robust dark matter halo, an invisible shield that provides the deep gravitational anchor holding the galaxy together. Without this dense, compact core of unseen mass, even the slightest collision would tear a galaxy apart. The trajectory it takes is equally vital, a favorable orbital path that turns a potential direct hit into a survivable glancing blow. High-speed, elliptical orbits allow a galaxy to swing past the worst gravitational stresses, using its own momentum as a defense. Internally, a high-velocity dispersion gives the galaxy resilience, the frantic, random motion of its stars creating a form of pressure that resists being pulled apart. And finally, the presence of gas acts as both a lifeblood and a shock absorber, a cosmic cushion that can absorb the energy of impact and even trigger new star formation. We see this intricate interplay in action with the Large Magellanic Cloud, a satellite of our Milky Way. It possesses a significant dark matter halo, travels on a wide orbit, and its abundant gas allows it to not just survive its gravitational dance with our galaxy, but to thrive, actively forming new stars from the encounter. This synthesis reveals that survival is never about a single factor. It emerges from a specific, harmonious combination of conditions, where a weakness in one area can be compensated by a strength in another. Understanding these mechanisms does more than explain the fate of tiny galaxies. It grants us a profound window into the universe's grand evolutionary processes, showing us how structure and chaos interact to shape the cosmos we see today. Our journey through the cosmic dance of survival reveals a universe where resilience is written in the language of dark matter, sculpted by orbital paths and tested by the fires of creation itself. We have seen how an invisible shield of dark matter acts as a gravitational anchor, how a high-speed glancing blow can spare a galaxy from total destruction, and how the churning motion of stars and the cushion of gas provide vital internal defenses. These are not isolated tricks but interconnected strands in a single, elegant web of cosmic endurance. The faint, enduring glow of a dwarf galaxy is more than just a pretty sight, it is a profound message. It tells a story of ancient mergers and close calls, a living fossil that holds clues to the universe's earliest structure and the mysterious nature of dark matter itself. These galactic survivors remind us that the cosmos is not a static museum, but a dynamic, ever-evolving arena where chaos and structure are locked in an eternal embrace. If this exploration into the heart of cosmic survival has ignited your wonder, consider subscribing for more journeys into the universe's greatest mysteries. We would love to hear which facet of this galactic saga fascinated you most, so share your thoughts in the comments below. The universe is vast and full of wonders, and the next great discovery is waiting just beyond the light of the stars.